All right, so elephant's toothpaste. This reaction is what's called a decomposition reaction. So when something decomposes, like what do you think of it's doing? Dissolving, breaking down, right? In chemistry, decomposition reactions are when things break down. So this is hydrogen peroxide. What do you use hydrogen peroxide for?
Clean out your sore.
Clean out a sore, and it doesn't feel very good, does it? Now the hydrogen peroxide you would use for that is only like 3% concentrated hydrogen peroxide. This is 30%. So if this touched your bare skin, it would start to eat away at your cell membranes. It would oxidize and bleach your tissues. It'd be really bad. It's almost like an acid in that sense, but it's not a very strong acid. It's really weak. It comes in this funny little accordion container so that if it drops, it can't break because it's super dangerous, kind of. But you guys aren't in any danger, don't worry. So anyways, this is 30% hydrogen peroxide. I don't know if I said that, so we'll put that in here. Now hydrogen peroxide, have you ever heard the joke? Two guys go to a bar, one says, I'll have H2O, and the other guy says, I'll have H2O too. The second guy dies. Have you ever heard that joke? Yeah. The chemical formula for hydrogen peroxide is H2O2. So what's going to happen is we're going to decompose it. Now when you put hydrogen peroxide on your skin, it starts to bubble. What's actually happening is oxygen gas is being made. That's what the foaming sort of is. And then the hydrogen peroxide is being neutralized and turning into water. So that's what's going to go on in this reaction. We're going to make water and oxygen gas. And it's going to get really hot. Because with energy, you can't make a reaction take place without energy. When bonds are formed or when they're broken, there's energy released during that. So some reactions they're not very energetic, whereas others are. And this one's quite energetic. This stuff is potassium iodide. Now, potassium iodide will not physically react with, or it won't chemically bond with the hydrogen peroxide, but it'll speed up the reaction, right? It's called a catalyst. And I'm gonna add what color do you want? Blue, yellow, red, or green?
Green. Not blue.
I did green last block.
Not blue.
Look at that. Well, whatever, that'll work. It kind of got all janky on me. Anyways, 5, 4, 3, 2, 1. Ta-da! Now, that'll keep expanding on us. Now, the reason now do you see the smoke coming off of it? That's the heat, so it creates a lot of heat. Now, the soap is why it got all bubbly, but what's inside those bubbles? Oh, shoot, the fan blew up my flame. What's inside the bubbles? Oxygen gas, right? So we can test the oxygen by seeing if it burns. Which it ought to. So this is just a swab with alcohol. So even though these are soap bubbles, they're filled with oxygen, so they burn, right? Nope, I put it in too deep and it extinguished itself, but whatever. So there you go. All the smoke coming off of this, that's just the heat, because like I said, now that hydrogen peroxide will just naturally decompose, but I sped it up. When you speed up chemical reactions, sometimes you either have to add heat in order to speed it up, or when you add a catalyst, which is what I did, the reaction itself just naturally speeds way up. So if I sort of dig this out of here, it's really, I'd like you to touch it, but it's got this hydrogen peroxide stuff on it, but it's really hot. Like it's actually really, really hot. I have some thermometers, but I'm using them for something else, so boom, there we go. America is kind of famous for fireworks, right? Because we have a holiday where the entire point is to shoot fireworks and drink beer and fall off a boat, I think, too, is the other thing that people do. So anyways, but where did fireworks come from? Who invented them?
India.
Nope. Benjamin Franklin. China. China also invented what other kind of, yes, they also invented gunpowder. They also invented paper. They also invented scissors. They also invented the modern plow. They also invented.
Modern day dodgeball, which used to be throwing severed heads at each other.
That's fun. Anyways, so magnesium, so fireworks are really cool, but you can't just blow up gunpowder and get like firework displays or whatever. Instead, they have to put materials that burn for long periods of time and that can burn multiple colors. And different metals will burn those different colors. And magnesium's one of them. Magnesium's kind of a cool one. It's not colorful, but it's very bright. So this is what we call a synthesis reaction, right? So magnesium and oxygen are going to react together and form magnesium oxide. So the oxygen for this is in the air. Now if I leave this magnesium for a really long time, it'll eventually get all dull. It'll have oxygen bonded with it. And we can call that oxidation. Like bridges and stuff do this, right, as they form rust. But I can add a little bit of energy to this and get the reaction to speed up. This might take a little bit of time. Come on. There we go. So it's very bright because it's magnesium. Yeah, it's like a sparkler. Sparklers have magnesium in them and a few other things. Boy. But when it's all done, why did I look directly at it? When it's all done, you can turn the lights on for us. Thank you very much. That ribbon is still here, but it's a different material now. It's magnesium oxide. And if I take magnesium oxide, where'd that thing go? Went too far. I can do kind of a test with it. So if I take it and break it up into little pieces here. So magnesium oxide is just like a white powder. But it's basic. It drinks pumpkin spice lattes and wears Uggs. So if I dump this stuff called phenolphthalein in here, phenolphthalein, oh, it didn't really do anything. When you mix basic materials with phenolphthalein, they change color. I'm going to set this off to the side and see if we can get that to pop up for us in a little bit. But I can do two different demonstrations here. So I'll take this. And this. This stuff is called bromthiamyl blue, and it's used just to test acids and bases. Phenolphthalein is used to test for bases, whereas the blue stuff here is used to test for acids. Acids and bases are, well, that wasn't supposed to happen. Well, anyways, that totally wasn't supposed to happen. You see how I just changed color right there? So I diluted it with water, but there must have been something mixed in there that that was basic. So it changed color. That's what it's supposed to do. Now this one, hopefully, doesn't do anything.
Hopefully.
Okay, good. I just want to dilute it a tiny bit. So I was going to add something to that to make it change color, but it decided to do it for us. And that's okay. What I can do now is I can alter this. I can make it go back. So it's basic. So if I add some acid to it, I should be able to make the color disappear again. So we'll put it in front so everyone can see. So it should go back to, oops, that's the wrong material. It should go back to clear.
Are you about to explode?
No, it was the phenolphthalein stuff again. So this is just hydrochloric acid, which you don't want to drink either. Boop. There we go. Goes back. Now this one is a little bit neater. I got to be kind of careful with it because, come to think of it, I'm going to dump a little bit of it out. So we're just going to forget that ever happened because I'm not going to use it. Okay, so let's get this stirring. And look at this carefully because it's kind of cool. I'll add a tiny bit of acid to it.
You should put it in slow-mo.
Ta-da! So it goes from blue to yellow in the presence of acids. If I don't know if this will work, but if I take a basic material like cleaning agent, it might a little bit go back to blue, but probably not. A little bit. You see how it's diluting the color of it a bit? But if I go ahead and add a lot more acid to it, let's actually dump a tiny bit of that out. If I add more of this, it should turn like a deep orange because I'm making it more acidic. Not quite. It did last time, but not quite. I had more concentrated bromothymol stuff. So that is a chemical change. What's the difference between a physical change and a chemical change? Or a physical reaction and a chemical reaction? Sean?
Physical is still the same thing, but now it's different.
Yes.
Chemical can't be.
You can't undo a chemical reaction, right? Like when you bake a cake, the egg protein, the flour, the sugar, the water, those, when you have your raw cake batter, it's egg protein, flour, sugar, all that stuff. You can't really pick it apart, but it's there. It's in its like pure form. But after you bake it, you chemically alter it, you add energy, and the molecular bonds between those things interchange. And when you pull your cake out, there's no egg protein left. There's no flour left. It's been bonded and turned into something else. If you put cake in the freezer to unbake it, do you get eggs and flour and sugar and water and yeast? No, it stays the same because you can't undo them. Awesome. So this is just like purified water, nothing special. So also in chemistry, some materials we say are highly reactive. They have a high affinity for bonding to things. Oxygen is one of those molecules. Oxygen is super excited to bond to other materials. Oxygen is always looking to hook up, right? Oxygen's kind of tramp. But other materials are not like that. So you guys, anybody know what the noble gases are?
Barely.
Nitrogen.
No.
Fluorine.
No.
Noble.
Helium, argon, krypton,
Neon.
neon, and xenon, or xenon, or whatever it's called. Now those materials, they're all the way at the right side of your periodic table. They can't bond with any other atoms, not even themselves. So they always stay as individual atoms, and they can never form compounds. Oxygen, the reason that rust happens and many things, oxygen is super reactive, so it just likes bonding to other things. Some materials that like to bond, they bond really slowly, or they change chemically very slowly, but others change very quickly. And this is an example of an extremely reactive and fast reacting chemical reaction. So sodium is a metal. If you look all the way at the left side of the periodic table, it's the third one down. So this is it. It kind of looks like a metal, but it's really weird. If I take it and I squeeze it, I have to use 2 fingers. It's squishy, right? But it's kind of stiff. It's like if you left a gummy bear out for several days and then picked it up. It's kind of like that texture, but it's soft, so I can cut it with a razor blade really easily. Boom, so there we go. Now if I cut it in half, you can really see kind of the reflective metallic look of it. The outside of it gets dirty really quickly because it's highly reactive. Put your goggles on. Not only do they make you look cool, but they keep you safe. Ow. So sodium hates water. It absolutely hates it. I like water. I drink water and it makes me happy. But when you put sodium in water, if you look at the board, that's what's going to happen. So this is going to split apart the water molecules, and part of the water molecule is going to bond to the sodium, forming sodium hydroxide, I believe that's called. And then you're going to hear fizzing, and the fizzing is hydrogen gas forming. So don't need that. Boom. So if you want to stand up so you can see, it's turned into a perfect sphere because it's molten. So it gets incredibly hot when it touches water, and it turns into a molten material. And it's just going to fizz around until the entire thing has been broken up into hydrogen gas and sodium hydroxide. Sometimes when you do this, it'll actually catch fire. And sometimes when you do this, it'll pop and the thing will explode. But this shouldn't because, well, it did on me one time last year, but this one won't. But sometimes, yeah, while it's sitting in the water, it catches fire. If you go on YouTube, you can watch videos of people doing this kind of thing. If you take something like cesium and do this, if I would have put that much cesium into this, the entire thing would have exploded just right away. Like every one of us probably would have had glass in our faces or something like that. Now you can't really get cesium unless you special order it and you have a license. And I definitely don't have any. And even if somebody tried to give it to me, like, hey, do this in your science class, I'd be like, no. Although you could just like chuck it into a lake and watch it explode from afar. Go on YouTube, you can see videos of people doing that. You can turn that on. So inside of here, it's what we call an aqueous solution of copper 2 sulfate. So we all know what copper looks like. It looks like pennies. When you bond copper with sulfate, it's this kind of pretty lapis lazuli sort of blue color. Just put that back in there. Looks like candy, but it's not. So I just dissolved it in water here. So what we're going to do is we're going to put aluminum, just raw aluminum foil, pure aluminum, into it, and it's going to do a replacement reaction, what we call a single replacement reaction. So I'll roll this up so we have lots and lots of surface area. I'll just put that in there for now. So if we look here, a single replacement reaction is, say there's a couple and then there's some guy, he's all by himself. He's going to replace the one guy, so now top hat guy is the sad guy, right? So what happens in this reaction is we have solid aluminum all by itself, and you can see it's not doing anything. This has been in here for over an hour. So if you look, it's being chewed away. Now do you see the patina that's on there? That's copper. So what's happening is the aluminum is trading places. The aluminum's going from solid mass to dissolved in the water, and the copper is going from dissolved to solid mass collecting here. Now, if we leave this sit here, it'll do that because, I mean, that's what it's doing. And if we check the temperature, where did my thermometer go?
Right up there.
Oh, thank you. If we check the temperature inside there, it should just be room temperature, which is nothing special. I'm going to put this inside the aluminum. So it's at, this one's a little warm because it's been reacting. It's at 87, 88 degrees. This one is just a little over, it's about 82 degrees. Now, this is eventually going to turn into that, but that's no good. So what I want to do is speed it up. And I can speed it up by adding what's called a catalyst to it. Our bodies make these catalysts, and we call them enzymes. But you can make a catalyst for just about anything. So I'll dump in some hydrochloric acid. And very soon here, this should start fizzing and getting pretty reactive. And it's doing it right now. Can you see that? So it's going to start to get really hot because, kind of like before, I'm forcing the reaction to speed up. So what that does is it adds a lot of energy to the system and it heats it up. So this will get to, you know, around 105, 108 degrees or so as we let it go. But if I pull this out of here, see how the copper's already forming on there? So really quickly, atom by atom, the copper is being pulled out of the solution and just turning into raw solid copper. That's going really quickly. That's going a lot faster than it did last time I did this. So anyways, pure aluminum, and now it's being turned, as it turns into copper, it gets all crummy. And so it sits there. So this one is already, it's already at 97 degrees. This is already sort of gotten to this point just about. This has been sitting here for over an hour. This has been in there for about 45 seconds. So those catalysts are really important in speeding up reactions. Some minerals, like diamond, can only form deep inside Earth's crust. Why the heck is that?
Extreme pressure and heat.
Yep. It can't form unless there's really crazy heat and pressure. You're exactly right. 107 degrees already. Anybody want to feel it? It's not dangerous. I'm gonna hold it though. Feels like a cup of coffee. Anybody else? Okay. Okay, so go ahead. So this is potassium iodide again. So we're looking all the way to the bottom. This is a double replacement reaction. So we have one chemical compound which is like AB, the sodium iodide, and then we have the other compound which is like CD. I'm gonna write this on the board so it makes sense. What we're gonna do is we have one compound AB, so that's like lead nitrate, and we're gonna make it react with the other compound CD, and what that's gonna do is form ACBD. So they're both gonna be separated from each other and then form a brand new compound. And this one's kind of cool. What will happen here is we'll add just a little bit of lead nitrate to this, and make sure you can see this one because it's really cool. And it happens instantly.
I can't see it very well.
Move your tubes, bro. All right, anyways, so when I dump this in here, it's gonna change instantly. It's not gonna get hot or anything like that, but it'll change color, and as I dump this in, it'll create a solid, like instantaneously. I'm gonna mix two liquids together. One compound will still be liquid, the other will be a solid. Why don't I just hold it up here and I'll do it. Make sure it's in the frame of the camera. Okay, ready? Isn't that kind of cool? That yellow cloud that formed there is, I don't know which compound it is, but that's the solid substance. If I let this sit here for a while, we'll just see this cloudy, or this chalky yellow layer of stuff on the bottom. That's the solid compound that it made. And then there will be sort of a clear material on top.